sub of TG, as we've seen that this is injective. So certainly we have the restriction mark from rep TG to rep G. Restriction. But also we have this map, the defining map, from rep G to rep TG. Which is, I mean, every representation space of G, V, becomes a representation space of TG just by restricting TG to that vector space V, right? So this is defining. So basically,
can you restrict to the smaller vector space?
if you have a representation of, sorry, this is not a smaller vector space. This is just group restriction. If you
this is okay. The one below.
So if you have a row from G to GLV, this is some representation of G, I want to claim that
the second one comes from the fact that the initial transformation defines
that there is a map from TG to GLV, taking a U sequence to U at 1, which is and actually in GL we've seen. So this is just the coordinate wise. So this is the defining property of TG. So this is like this name. So basically, you know what I want to say. I want to convince you that these two are the same as this. It must be the same. And these are facts about the representation theory of compact groups, which I don't want to say too much about right now. I want to say. So I want to say that the way to view those things is to show that this guy, OG and OTG, are the same. And then to show that TG is not bigger than G. If G was a compact closed sum of TG, then I could find a function, a continuous function, I don't know, positive continuous function on TG which does not meet the G at all. And I claim that I could integrate it in here and get some positive value. Also, I can integrate some functional, some polynomial, some guy from here, approximating it and get some positive value. But its integral in here must be 0. But the integration is just the same as the integral, as you know, in Pontryagin duality. Evaluation on the identity in one group is the same as integration on the other group. It's the same here. Integration on G is the same, and at this point of view, is the same as take a function here and project it to the trivial. So it has a natural projection to the trivial representation over here. So this is a new function, but actually a constant function, and this constant function is the integral. So I'm saying that once we know that for two groups, G and TG, you have the same representation ring, then also I can integrate functions. The integrate function is just the same. If I have a function here, I can integrate it in TG, I can pull back to G and integrate, and I will get the same value, and this means this must be surjective. Again, without, I don't know. going too much anymore. I did start writing something before, and I want to complete it. It was wrong as I studied it. So what was it? So if you take the endomorphism of F, maybe respecting direct sum, so I wrongly brought them up to O, which it should have been to the product, as regrettably, of all endomorphism of lambda. And I claim this map is easily seen to be an isomorphism whenever I have an endomorphism. A map here is an endomorphism of HV lambda, of course, in particular. So it has a clear image here. And to see that it is onto, is there anything? I just want to remind you that the canonical way, if I have a V, then it decomposes canonically as direct sum of a lambda of V lambda tensor V lambda V. This canonical identification. So these are the isotypical components, and somehow this is the multiplicity of the component. And if I have an element here, so T lambda, T is an endomorphism of each component, it clearly acts on this one. So, and then this is canonical, or maybe if you want, by conjugating this action here by this isomorphism, I get an action here, and this action will be compatible with everything here. Now, so this is not that algebraic direct sum, this is a direct product, it acts on the direct sum. Act on OB. This is direct sum of V tensor V lambda. OB. It acts by precomposition, if you wish, or acting on this postcomposition, whatever. Choose a sign. And there is another action, commuting action, of the same kind. Just one. So I act here, and actually, so somehow this is the double commutant that goes on, right? In here, we have and it commutes with everything that commutes with it. Now, I want to say something, and I will not justify every word I'm saying, but I want to tell a story. So if I will get a bigger group here if I will not insist on commuting with complex conjugation, right? I thought it would still be a group. It will still be a topological group, but I will just forget an abstraction restriction. So I'm getting some bigger thing. I claim that this bigger group will be the complexification of mine.
Why is it a group?
I mean, the fact that the fact that not
Just the compactness.
just the compactness we used the conjugation, the complex conjugation. That was about duality, V star. Remember the dual of UV was this star has nothing to do with complex conjugation. This is the duality star.
Okay.
Yeah, I should maybe use different symbols, but it's just the dual vector space. So there is maybe another group. Shall I give the name? GC. get if I take the same defining properties of TG, just not asking for commuting with complex conjugation. Now, so far, my group G was in this discussion compact, but I never said that it is a matrix group. Right? In our previous discussion of complexification, we were talking about matrix compact group, and we showed that they are algebraic. So, what kind of difference in this picture will it impose if I have a matrix group? Maybe some of you will see it at once. Otherwise, I will say and leave it as an exercise for you.
Can you ask again?
Yes. I'm saying that in previous lectures, we discussed compact matrix group, compact subgroups of G and C, and said that these are all real points of algebraic complex groups for some real structure. And here in this discussion, we did not impose this condition. G was an arbitrary compact group, and I claim that there is an clear algebraic difference if I do impose this condition. It will give me some extra piece of information about this picture. This piece of information,
Impose which condition? What condition?
that if the condition that G is a matrix group.
Ah.
It will be something about the algebraic structure of this type. So this will be finally generated as an algebra, if and only if G is a matrix group defined by finitely many polynomials. Oh. So those polynomials, actually, although the matrix coefficients of some injective representation, if G has one finite dimensional representation which it injectively representing, right? This is this condition. The matrix coefficient of this finite dimensional or this very matrix representation, or maybe the irreducible components associated with this, some finitely many things here, will generate the ordering. And this is if and only if. And I leave this as an exercise. So in that case, I will get something very nice. Because these are all functions on G. So as an algebra, this is an algebra with no problems. And if it is finally generated, this is the fine algebra of some variety. There is a spectrum, not in the Gelfand sense, which is G, but in the algebraic sense, which is this. Okay? And again, I will not prove everything. Maybe I'll explain.
So CG is just formal linear combinations of elements of G.
No, CG is continuous functions on G.
Continuous function.
Continuous functions on G.
And this you call the group algebra?
No. CG is a group algebra. No, I didn't discuss the group algebra. So when I say that, it sounds just the same. This extra line.
But what is finitely generated? Which subalgebra is finitely generated?
The algebra, this algebra,
The OG.
OG, is finitely generated algebra if and only if G has an injective representation. I mean, all the representation together are always injective because representation separate points. This I know. But it might not be, there might not be a unique one which is which generates everything. Unique finite dimensional subspace here which generates everything. This is if and only if you have an injective one type. And again, if this is the case, then this is the polynomial algebra on some algebraic variety. I claim, just by general notions. And this algebraic variety will be a group because of some algebra that I have here, which I did not discuss, but it's kind of in the theory. You see, So it might be a complex group, and so I want to emphasize this point in order to explain why is it that the notion of complexification is so canonical. As we presented it last time, it was some unhooked manner. G is a compact matrix group, then it has a complexification. But really, you can see it very clearly from the structure of G as double dual construction. And again, I will not explore all the details. I can give you reading material if someone is interested in reading further. So this is called Chevalier duality. Or if you wish, Chevalier duality is what if I started with this complex reductive group, and I look at the category of complex algebraic representation of it, and take double dual, without this conjugation thing. Then I will retrieve the same guy G, same guy GC. This is Chevalier duality. And what we see here is Tanatian's Chevalier duality. Start with a complex guy, go back and forth, forget the conjugation invariance, you get the complexification. Okay, and again we can see it in the level of representations, which is absolute level. We can see it, maybe it is better, more down to earth, to look at, say, for Chevalier duality, I will look at this ring, OG. Now this is a standard OG associated with this algebraic variety, polynomials over it. And I will look at all automorphism of this ring that commutes with the right regular action. And I will retrieve the left regular action of Q itself. I will retrieve Q. Okay, is this very clear?
So G is still compact for you when you say matrix group? You only say complexification of compact group?
Yes. So, in fact, which we've seen, basically, every compact, or maybe, just maybe, what if I didn't have a matrix group here? This would not be finally generated. Still, this would be the direct union of finally generated subthings, right? So this means that this G that you will get will be, which is the same G, the duality goes in any case. Now, just looking at an active duality, forget the complexification. Any compact group, any compact group is a projective limit or inverse limit of matrix compact groups. It follows from this discussion. It follows figure 1 if you wish, but this is very nice. We've seen in the last talk that we discussed a bit profinite groups. Then it's projective limit of not just any matrix group, but finite matrix group. But in general, we can have a bit. We have a slightly more complicated thing. But every compact group has a complexification here, because this procedure that I described is completely canonical. Take G, take whatever commutes with that, and forget the conjugation invariance. You will get something. What this thing be? It will be the projective limit of the complexification of the finite of the matrix things. So it will be a true algebraic group.
So I didn't follow most of it.
I didn't say.
Yeah, I just want to make sure if I understood what is an exercise and what is trivial and what's not. So the fact that this O of G is finitely generated ring,
This is
if and only if your compact group embeds in a matrix.
Yeah,
This
is an easy exercise.
That's an easy exercise. So suppose I understand that, and then I know that my OG is a finitely generated ring, and hence the corresponds to some affine variety.
Exactly.
But then, why is this affine variety suddenly G of C containing TG? where did it land? Why did it land there?
Okay, so what is the spectrum of OG? I'm not sure I will completely explain, but let me try. What is this? This is home OG C. Algebra morphism. These are all OG are functions on G, on the original guy. Think of it as functions, because if you think of it, this already gives you some points here, some evaluation at some points. So, for example, you have here evaluation at the identity of G. Think of any elements of here in here as a function on the compact guy G. Evaluate this function at the identity. This is the algebra morphism into here. Here is the identity of GC now. I want to think. Now, I mean, this I'm exploring this guy. I'm claiming that this guy is a group, which is an algebraic variety. It's a complex algebraic variety. It's a bigger thing than that one.
Why is it even?
The fact that it is a complex algebraic variety is a fine variety. It's a general nonsense of algebraic geometry.
One or 10 steps behind. TG is, we had the definition of what is TG, but why do you think of?
Yes.
Okay.
This is canonical G.
Why is canonical G?
And here is a bigger object, which now I denote GC.
Why do you think it is a big object?
Okay, I didn't say, I guess I say, I didn't write down the definition of that then. Written here, I denote it as a complexification, but when I explain what I'm meaning, this symbol here represents all endomorphism of F that commute with direct sum and tensor products, and they are one at one, but without the extra condition that they are conjugation invariant. Okay, so this is this symbol.
Yes,
So this is
then
every.
it's obviously it contains TG.
Obviously it
and
contains.
it's a group, yes.
Yes, and I claim that there is a natural identification of this object with the spectrum of that one.
So that's the Chevrolet one.
And this is the Chevrolet one.
And my
yes.
question is basically, what's the identification?
Now I'm trying to, I'm explaining. So I claim that G act on the left here, right? So by this, I'm getting for every element of GC, for any G now in GC, I will get another guy here.
G acts on the left there, you say, but how does that, when I think of these as functions and then I just recompose or something? Or?
Automorphism of the ring. I claim that each element here that preserves direct sum and direct product, act on this ring by automorphisms. Claim. I mean, this is preserving direct sum and direct product is preserving sum and product in that ring. So in particular, G does. Oh, this is.
And if I think of OG as continuous functions, is that an action that I can describe?
Yes,
The
it's the left action.
It's just
It's the left regular action. Yes.
left regular action.
And what?
So you have a left action.
Yeah, so I have a left action here. So I also have a left action of the space of homomorphism. For every element of G, I can translate by G or apply this automorphism of OG and then evaluate. So I'm getting
Evaluation at G.
so this should be evaluation at G. Yes, this is another point which I would think as evaluation at G. So this gives me a map from G here, which one should check and see that this is an isomorphism. GC. Oh, this I didn't do.
No, but you just it
I
showed me
explained this
no,
map.
No. You explained the map from G to spec.
From GC. My G, in order to say it, I didn't have
This is why you actually needed the. to go through that diagram, and you couldn't just say, because I was thinking to myself, OG is continuous functions on G, truly on G, and then G acts on it.
Yeah, okay.
But
No,
you
so,
actually want G of C,
yeah.
G of C to act on it. And that's the
Yes, I want G of C to act on it. On CG, you don't have the action of GC. On C of G, you do have the action of G, and the spectrum, the Gelfand spectrum. So the space of all maximal ideals are exactly the Gelfand spectrum G.
So in some sense, this is the essence that you
Well,
find.
yeah,
You find
of
this
course, when you take
smaller,
when you take a smaller algebra,
you
you get
actually-
more homomorphism.
you
Of
can
course,
act on it by removing.
right? I mean, yes. No, it's not only yeah, but also you have. I'm having algebras and homomorphism to see. Taking a smaller algebra, you get more homomorphism.
But you mean this right hand?
So this, just a minute. So here you have this inside CG, and this is related to that, and this is related by taking the spectrum. Well, this is all maximal ideal of that. This is all maximal ideal of that. And the fact that this the inclusion here, the inclusion.
But this map here, this is equality by definition. I mean, you define an algebraic group G by the algebra OG, and its C points are just
But
homomorphic.
when I first defined this, I didn't define it as the spectrum of that. I defined it as some endomorphisms functors. So
That's the duality.
this is the duality. Yes, this is just the duality.
It's a bad choice of notation.
Yes, the
Or-
bad choice
or
of notation.
G of C.
My choice of notation already assumed the duality. So yeah. But this is Chevalier. I mean, it's not a tautology. Oh yes, it is tautology. It's not a reality. It is the reality as well. But I should have say I draw 2 or 3 more lines. You know, do this, which I will not. I will get confused. But there is no. This is not deep at all. Nothing here. Maybe except Peter High.
Even then.
So what is that I want to say? Oh, and now I claim that this GC is the same. Is the complexification of the guy G that we've seen before, because well, we already now this is an exercise to put these together. We already know that this is the real point of some complex algebraic groups, and this not in a canonical way a priori, but these complex algebraic groups, that this is the real point of it, must be the same as that one.
So how did you define it last week?
You
Just quickly.
last week I took a compact matrix group. So it's some compact group inside GL and C, say. And show that this is the zero set of some polynomials defined over this. So you can sorry, in GL and R. And look at all polynomials that vanish on G, and take the common zeros of these. Of course, G is included there, but it is very easy to see that nothing else is there. G is exactly the spectrum of the ideal of polynomials that vanish on it. So it means that G is GR of some complex algebraic group. This is the algebraic group defined by these real polynomials. So this happened last week, and then this was just about concrete representation, injective representation of this G in here. There was nothing canonical in it, but now it is rather easy to see that this GC must be this one. Okay, which I'm with you.
Why is this not canonical? Because it depends on
Because,
the choice of.
This depends on the embedding of G and G. If you think of a compact group as some abstract thing, the choice of complexification or decomplexification was depending on some inclusion here. While
somehow
CG is some canonical construction on the topological space of topological group G. This is a topological canonical subspace, and the spectrum of it is something canonical, and this is the complexification.
How could it be that you would be able to miraculously, in a tautological manner, show that this G of C, which is not a priori not canonical, is the same as that G of C? It seems as if you can do that, then you can show that any two such G of C's are the same. Also, without
Well,
this
let-
discussion.
It's very easy to see, without this discussion as well,
That it
that,
is canonical.
that it is canonical. I mean, it is canonical in the sense that it does not depends on the representation.
Yeah, that's what I mean.
Yeah, what I did here is a bit more. I explain, I show a roadmap how to canonically
Define.
construct it. Yes. So yes, you can.
But the same hidden in this exercise that you leave us is in fact included to show the fact
I
that
mean, you may say so, but actually, it will give you
But you mean
a considerable shortcut.
the R points of these two algebraic groups are the same. So doesn't it follow that the R points are the same?
So the-
I mean, a priori you get two algebraic groups, but the R points are the same because they're both the G.
Okay, so you're starting proving, solving my exercise.
Yes. And that wasn't, I mean, your question, right? Why?
Oh,
is it the same?
no, I said that I will not give the details, but
Okay, yes.
what I intended to do here is to tell a story of how things could be defined very smoothly. Here I didn't want to give all the details, so you are invited to fill the gaps. So just wait. So what is the so I started writing every compound. Yeah, every compound. Thanks. Every compound matrix group, I can erase compound, and then instead of algebraic, I would write algebraic. Matrix group is in GLNR is the real point or every compact maybe group which is isomorphic to a matrix group in GLNR is the real points of a reductive complex semifinals. Then such, so you get a reductive complex group, but you get more. You get a real structure on it. A priori, when I'm giving you a complex variety, when I'm giving you a complex vector space, there is no conjugation on this complex space, right? I can define V bar as a D for you as another object, but it's not the same object. If I identify V bar with V, if in the vector space I do identify a real sub-vector space of the same dimension, then I'm getting you a complex conjugation on that space, right? And then I can, if I have a group sitting in it, or a variety sitting in this defined space, I can talk about the real points of it, the conjugation invariant points. A priori, there is no real points for a complex variety. In order to have a real point, I need an extra structure. So here I'm given not just a complex reductive group, but also a real structure on it. And this real structure, such a real structure, I'm using the language. Instead of saying such a real structure, I will say such a compact group. such a group GR is called a compact real form, or sometimes anisotropic. We already seen that there is a relation between isotopicity and compactness. Anisotropic real form. Of the given group. Okay. So this is basically more or less, by now I'm at the end point of the last lecture. Everything here was just, again, a summary just to see that those things are quite canonical. And of course, I didn't say all the things that I wanted, and you're encouraged to read further. And I can give you references if you wish.
Will we see why it's productive?
Yeah, so someone want to say why it's productive? We've seen that, well, a group is reductive. What's the definition of reductivity?
So we see center.
This is not the definition.
Any representation.
Oh, okay, this is sometimes easy.
That's a
This is sometimes definition, but this is not the right definition.
So
For
this is
example,
giving
it is
more
not, it is
without
not
general-
coincidence definition with
This-
characteristic.
Ma treba important velik.
Hmm?
Treba important.
An algebraic group, so determining the definition, is reductive if its unipotent radical is trivial. Maybe a mark. G reductive implies, so unipotent radical is the biggest unipotent normal subgroup. Unipotent subgroup is a subgroup consisting only of unipotents in the connected component, right? So there are no unipotent normal subgroups. G reductive.
What do you mean in the so if
Reductivity, I mean, you made in characteristic 0, unipotents are always in the connected components.
but you're trying to define something in any also in positive characteristics and
Yeah, so this definition is general.
but now you said you're defining to us what is the unipotent radical and
Unipotent radical,
from the definition that you just said, the unipotent radical in positive characteristics is always trivial.
no,
That's what you said. You said it's
there is a connected component.
Okay.
Yes.
No, you're right. You're right. I was.
But unipotent radical, maximal, normal, unipotent subgroup in G0, in the connected component relative. Again, over the reals, a unipotent is, I mean, the additive group of the reals is connected no matter what. It doesn't have any finite subgroups in it. Same for any group in characteristic 0, even though they don't look connected to our house of ice. But over FBT, say, or over any field of characteristic P, unipotent group might be finite, might be not connected. So we should be aware about it. The kernel of GA X to the P is the unipotent group of order P. So, now
reductive implies G0. A reductive connected group is always its center. Okay, it's getting, since I didn't assume that G is connected, take the center of the connected component times its commutator. So this is a semi-simple group, and this is a torus. And the intersection of these two guys is finite. So of course they commute. So there is a cover which is the product of these two groups, and this is an isogeny. It's a finite one cover. This is one remark, so this is what Alex wanted to give us a definition. So one can give it as a definition, but this is less canonical, I would say. And another, this works on patristic zero. A group is reductive if and only if all representation are, do we say completely reducible? Completely decomposed into irreducible ones. What is the
reducible.
Sorry?
Completely reducible.
Representation decomposed naturally into irreducible ones. And for all the complex numbers, how do you prove this? Where is it? The most classical way, which is what I want to do today.
How do you prove what?
It's hard.
These are the even only
Desimplification.
the algebra semi-simple.
I mean, actually, the other part is very easy. If you have unipotent radical, it's very easy to construct things which are not completely reducible. And so the Lie algebra is not semi-simple, there is a torus into it. Okay, do you know the historically the first proof of this fact? Via unitarian trick. So this is exactly, this is not what how Weil thought of it, I guess, but this is exactly what we do now. We unitarian trick. What Weil did when he wanted to prove this is to find a compact group inside a given complex group which has the same representation theory. And because the representation theory of a compact group is completely reducible, so it will be for G. So this is exactly the other side of this. So I guess this is there. But I'm not sure this is this vibe. I think also Moscow is the first one to really do it properly. So every I didn't answer the question. So I started saying this because of a question, and the question was yes, Max, why is this reductive? And so we have an anisotropic group, and I claim it is reductive. And we learned some things about anisotropic groups. Remember? When a group is compact, if and only if, in general, before we start doing things over the complex or the rings, so we spent sometimes on proving the theorem that a group is compact if and only if it doesn't have any split soluble subgroup, right? Over the complex numbers, unipotent groups are always split, right? So a
copper group cannot have unipotent radicals. It must be reductive. I think I actually wrote it as a corollary when we discussed this. In particular, in characteristic 0, compound groups are reductive. Remember this line. Okay, check your note. Every complex reductive group has a reason. Recon. All such are conjugated. So G act naturally on the space called complex formulary. I will rewrite this in a way which is, I think, is more familiar. Maybe some facts about complex. So here I wrote the definition of the complex form. I guess I wanted my notes to discuss this a bit before I could the theorem and somehow move to this. Claim. So G is complex algebraic. K inside G is compact and there is evidence. I claim that in that case, K is a complex form. Of G. Or more formally speaking, there is a ring structure on G such that K is the real points. And G is its complexification. So maybe in particular, as before, G must be reductive. I assume this is one thing. It can't happen otherwise. That you have a compact, so risky that's that. Okay, why is it? In K sits in G, it has some. Look at this fact. It has some complexification, so it is the real point of something. This something is the complex spectrum of all the polynomials that vanish on K, right? So, but K is a risky dense, so it must coincide with G. So this something must be G. So also. Now I want to write a corollary of this, or maybe equivalent, given this observation. So now I think I want to say this claim in order to explain in a better way what do I mean that they are all conjugated. The case that I find anyway the Zariski dense compact subgroups of G are all conjugated in particular. Right? So the claim here is that exists. I'm rewriting using this language. K in G, which is compact and Zariski dense. And these are all conjugated. And now I want to restate things, or to write down the corollary of the theorem. I didn't prove this. To write down the corollary in a language that I think you do know, you heard of, some of you at least. Compact form of G is the same as maximal compact subgroup. So, of course, if you have K, a compact Zariski dense subgroup, if you have a group which contains K, it will be compact and Zariski dense as well, so it will be another compact form, but they need to be conjugated, and one includes the other, and everything is algebraic. It can't be. I mean, for absolute groups, I can maybe put one isomorphically, a group inside itself. But I cannot do it for algebraic groups. Something must be dropped, dimension, number of components or something. So I can't have it. So I can't have a K, Zariski density, in another Zariski dense, while both of them being conjugated. So it means that every compact form must be maximal among all compact subgroups. And all those maximal, and there is a unique conjugacy class of that such. And right, all maximal compact subgroups are conjugated. So I bet this is familiar to some of you. And this all follows from the fact that there exists, well, not only the existence, there exists and all conjugated compact form, this algebraic fact. And again, this algebraic fact says that this Anakin-Chevalier duality is indeed a duality theory between these two classes, compact and complex reductive. We found a way of classification to go, given a compact group, to go to the complex reductive group. The way back is not a tautology. As far as I know, I don't know of an easy proof of that. I mean, it's not that the proof is super hard, but it's not conceptual. It uses structure theory. And I think something is missing, probably. As far as I know, there is no known easy proof, and there should be. So I think we don't understand things well enough yet. What is the time? I want now to start proving this, discussing this.
Research.
Is this tea?
There's nothing.
No tea today? Okay, but break. We can anyway.
So you're going to prove what?
So now I'm going to prove it. In some parts I will be a bit sketchy because then it requires a bit of structure theory. But I will give essentially all details and